Welcome to the webinar Machine Optimization with ANSYS optiSLang. We have the following outline. After a short introduction to optiSLang, I will discuss the point process integration, how we can connect your individual solver, your simulation model to optiSLang, and then we will discuss the design of experiments and sensitivity analysis, followed by a multi-objective and single-objective optimization. This is done by means of a machine tool example, and at the end we will summarize our webinar. My name is Thomas Most. I'm a member of the Dynaro company in Germany. We are developing the software optiSLang. Let me shortly introduce optiSLang to you. When we have real-world simulations, then usually we need significant computational resources. Then the parameter variation becomes more and more computationally demanding. Means that we are not able to run several millions, thousands, or whatever designs. We have to capture physical phenomena from several disciplines, which may be coupled nonlinear and even higher dimensional. So we have to consider many input parameters in our algorithms. And we have also to deal with so-called failed designs, means that we have the situations that some of the designs may be not successful in the creation process. Meshing may fail, the geometry tools may fail, and even the simulation itself. And in some cases, we may have license failures, which is a typical situation in real applications. So the algorithms have to deal with all of these requirements. We have to take care about many parameters, many input parameters, and we have also to take care about that the simulation model may contain some distortion due to numerical errors, so-called numerical noise. If you look on optiSLang, it's a general purpose tool for variation analysis, especially for CAE-based designs, and can be applied for sensitivity analysis, design exploration. On one hand side, we can calibrate simulation models to experiments or tests. We can optimize the performance of a specific product, system, or structure. And we can also quantify risk by using robustness analysis and reliability. And bringing optimization and robustness together, then we can perform a robust design optimization or design for Six Sigma. It's a special case of a robust design. So we have interface to arbitrary CAX tools. I will explain shortly. And we have some integration in the ANSYS workbench, which is quite comfortable for workbench users. We have developed the software with a philosophy that it's a toolbox for all of these applications, sensitivity analysis, optimization, and so on, which should be applicable for daily work by every engineer who is then maybe not the expert in all of this type of algorithms. So we want to predefine the workflows for specific applications. We have developed wizards, I will show you, which may recommend you some good settings, and we want to keep the algorithms running quite robustly. Means that they will at the end serve you some good result. So this was our aim, developing the software. You may have realized that if you already have tested the software itself. So what is our example today? It's a machine tool device which was developed by the Fraunhofer Research Institute in Germany together with the customer. And so it was already a manual pre-optimization done by engineering understanding, and they asked us if we could further improve this structure by automatic optimization. And we see here on the right side, this is the framework which is holding this device, where we have four spaces for the products which have to be manufactured, and then we have here a robot which is acting on this four spaces step by step. And it has to be considered that this machine holding device is turning around, so we have different load cases where the robots or the machine units will act on this device. So the customer was interested in having a high stiffness of this part, means low deflections, and of course lightweight, because then he could use much weaker engines to accelerate this device. So let us summarize what was the initial optimization task. It was the minimization of the mass, minimization of stiffness was measured in this case by the minimization of deformation. So we had 3 load cases in different positions, 0 degrees, 90 degrees, and 180 degrees. And we had an initial design of about 200 kilograms and about a bit larger than 0.1 millimeters maximum deformations in the middle. So how could we solve this optimization task? First, of course, we need some kind of a model, which could be analytical or simulation model. In this case, we used ANSYS mechanical to calculate the deformations in the 3 load cases, depending on the geometry parameter. So in ANSYS Workbench, we have the possibility to define a parameter set, which is then able to be connected to optiSLang directly. So we have a set of input parameters, we have a set of responses, which is then quite important for the further procedure. I will switch to the model now. So we have the ANSYS Workbench model right here. So we have the 3 load cases. All of them take the same mesh, the same geometry, and they have different loadings. So if we enter the simulation model, we see maybe this is some or one of the specific possible geometries. This is the reference geometry we see here, already meshed by shell elements. We have some loads in here. So this is the worst case, a loading of the second or third unit in this device. And then we calculate different positions by considering gravity in different directions. This is parallel to the load. This is 90 degrees. This is 180 degrees with respect to the load. And so we get 3 deformation fields, 0 degrees, 90 degrees, 180 degrees. And now we extract the individual response values by using this workbench functionality that we just can extract minimum and maximum values. We can simply add parameters by placing a P inside this checkbox. Now we extract these responses as well as the input parameters we have defined in the geometry. And now all of these defined parameters appear in the parameter set. This is the parametric environment the workbench offers us, which is quite helpful for parameter studies, optimization, and so on. So we have 4 outputs. We have about 60 input parameters for the geometry. So we considered several cross-section measures, the width, thickness, and height of the different beam cross-sections. So we considered for the red beams, we considered a thickness, a height, a width for all of them with the same cross-section measures. The same we did for the green beams, the middle beams, and the lower beams as well. So that's why we get at the end not 60 independent parameters. So we had at the end about 12 or 11 parameters, because many of them are collected together via dependencies in this workbench parameter set. So we get at the end the upper, the lower, and the middle beam cross-section measures, as well as the thickness of the upper plate of this structure, which is assumed to be aluminium, and the beams are assumed to be steel beams. And now we want to consider this in the first step in a sensitivity analysis. So we want to analyze what is the influence of the individual parameters with respect to the mass and the deformations, and how we may formulate an objective function. What would be a good compromise? Before we can do that, we need to connect a simulation model to our optiSLang software, to our automation process. So we just take optiSLang in order to communicate to the CAE process. So we assume that we have so-called design variables, which are the variables we modify in a certain range. That are the optimization parameters. Or we may also consider scattering variables, which should represent uncertainties we want to analyze in a robustness analysis. Then the CAE process is somehow treated as a black box, so we just modify the input parameters. optiSLang will execute the process, which may be not just a single model, maybe different models in a row or in parallel. And then we get several output variables from different domains if we have analyzed them. So we have available interfaces to almost all interesting simulation tools, FEM, computational fluid dynamics, electromagnetics, and so on. And if you have a solver which is just running in batch mode with a text input and text output file, we can make an aperture and connection to every type of that solvers. The minimum condition is that it's running automatically in batch mode. We can also provide custom integrations in order to support you with your own solver if it's not available in our already existing integrations. So one special solution is the Workbench plugin of optiSLang, then the optiSLang containers for sensitivity analysis, robustness, and optimization are available on the Workbench. And here we have a special situation since the Workbench provides, in contrast to some other solvers, already a nice parametric environment I have already shown for our example. So we have an overview of the individual parameters of the input side and the output side. This parameter set is available here in the Workbench project, and now we can easily connect our optiSLang containers, which are available after installing optiSLang, directly to the parameter set. So this is one possibility. So this can be used inside the Workbench, but we can also connect the Workbench model and running the Workbench in batch mode by using the so-called Workbench node. Then this can be combined together with different solvers, different CAD tools, different pre and post analysis may be a possibility. And we may also go a step further away from the standard workflows from sensitivity analysis, optimization, and robustness to that we may analyze a nested loop like a performance map or a coupled robust design optimization and so on. So then we can build up a much more complex so-called solver chain where we put together different parts of our analysis, maybe multi-physics analysis or whatever, together with one or more Workbench models, and then we can execute that in the standalone version in the user interface of optiSLang. Today we will stay inside the Workbench since the example is available completely in a single Workbench model. We will concentrate on how we can analyze this specific structure today. Before we can do an optimization, it's often quite useful to perform a sensitivity analysis in order to get some idea about how do the responses vary with respect to the given variation of the input parameters. How does the range of the input parameters influence the variation of the responses. This may help us later on to formulate a suitable optimization goal if we are not quite sure from the beginning. This will help us, as we will see now, to judge if the simulation model itself behaves well, means that with a variation of the input parameters, we can explain the variation of the responses. If some additional variation appears, this may be a reason of numerical distortion due to a very coarse mesh. We do automatic remeshing, and we collect response values which are not global but very localized results. So what is the overall workflow of that? We do some kind of a design of experiment, some sampling I will explain. Then we generate some kind of a Metamodel, which is an optimized specific type I will explain, in order then to judge which parameters are responsible for which response. So means that in the first step, a design of experiments, mainly filling up the design space, the space spanned by the design variables, is executed with our simulation model. And then we can use the data to test certain regression methods, finding out some optimal regression type, and then quantify the individual sensitivity. So what type of design of experiment schemes are available? Of course, we provide the classical DOE schemes, so-called deterministic DOE schemes. For example, the full factorial, which is nothing else than a multidimensional grid. But if we have more than three or four parameters, then the number of resulting simulation model evaluation increases dramatically with higher dimensions. So if we have just 2 points on the minimum and maximum value, and we have 10 parameters, and we have more than 1,000 samples. One way to reduce the effort is that we use more or less simple DOE schemes, but then we cannot really analyze complex relations. A much better approach is an Latin hypercube sampling, where we subdivide the space in classes defined by the number of samples we want to generate, and then we optimize the position of these samples in that way that the input parameter behavior is almost independent. Then we have to evaluate these individual parameter combinations with a solver, and then we can go a step further to analyze possible relations. What helps for that? Usually, a response surface method is a quite suitable approach for that. We can build up a so-called Metamodel and mathematical surrogate function in order to describe the relation between the input parameters and a response. We just take the points generated before by the design of experiment scheme, and we try to approximate the behavior between a certain response and the individual input parameters. So we have in literature a huge number of individual response surfaces approaches. What are we doing in optiSLang? We just collect the most suitable of them, and we just test them in like a challenge between them to find out what is the best suitable Metamodel for the specific case. What is a difficulty in applying response surfaces or Metamodels for higher dimensions is that with increasing dimension, we need more and more samples to get a certain accuracy. Or, on the other hand around, if we could find the important parameters, just the important parameters, if you have 50 parameters and just 5 are important, if we could find them, then we can represent the response much better with a smaller number of samples. For an objective judgment of all of these issues, we may need objective measure of the prognosis quality. There, it does not count how much does the model, the Metamodel, fit through the data. it counts how good does the model approximate unknown data points. And that we are doing by some kind of data splitting internally, some intelligent approach in order to estimate approximation quality in an objective way. Then we can compare the individual models and find optimal approximation model. We have put all this stuff in an approach, so-called Metamodel of optimal prognosis. It will use a so-called coefficient of prognosis as objective quality measure. It will determine the relevant parameter subspace. This helps to apply metamodels even for higher dimensions, for going up for 50, 100 parameters, and it will determine the optimal approximation type, polynomial, Kriging, whatever, linear, quadratic, and we have been careful developing this approach that we avoid overfitting, means that we have some quite general function in the approximation, and with help of this meta model, then we can evaluate the variable sensitivities. This approach is completely automatic compared with this slide where we have just mentioned different methods. You are not asked to do all this analysis by yourself. In the background, this approach is running quite fast to detect the most suitable meta model. Bringing the things together in a wizard, we have developed a sensitivity wizard which helps you to decide what DOE scheme is suitable depending on the type and the number of variables. How many samples are suitable? And then we automatically analyze what is the best approximation model for the specific response, what are the responsible input parameters, what is the necessary parameter subspace. This is done if the user uses the defaults fully automatically. We just need to type for the individual parameters available in the parameter set lower and upper bounds. And this works quite easily. We just take the simulation model, we connect the sensitivity module to the parameter set, then optiSLang is started in the background. We will get an overview of the available parameters from the workbench model, and then we have the possibility to enter lower upper bounds if you like. Here we get the initial values from the reference design. We can modify the bounds, so it can be between 40 and 60 in this case, and so on. We may change the resolution type. It can be a continuous, but maybe also a discontinuous parameter, which is 40, 45, 50 maybe millimeters for one of the cross-section parameters if you like. Yeah, those are the typical settings we have do here as a user, but the setup is usually quite easy. If you don't want to consider a certain parameter, you may just keep him constant. Then it's not considered in the sensitivity analysis or in optimization. We will import the parameters from a previous exported file because you can easily, in a certain project, you can easily export your parameters to a comma-separated file. Then you get maybe such a list from a. We just import all of these parameters, and now we get the setup we have prepared for that example. Yeah, so you can do this by hand, and you can export it the parameters, so you can just import a predefined comma-separated file. And then in the next step, we need to define the optimization criteria in the sensitivity analysis. This is not necessary in all cases. So if you don't know exactly what could be a good combination or whatever, we can keep this empty. In the first step, we analyze the dependencies between the response values and the input parameters. So we keep this empty in this step. Then there is a recommendation about a suitable DOE approach. This is in this case advanced Latin hypercube sampling. And then we get this container, which is linked to the parameter set. We need just to update the container, and then the analysis is running for all of these 100 designs which have been recommended by the DOE approach. Then the designs are submitted to the parameter set or the design table of the workbench. We can configure the remote source manager in order to run several designs simultaneously. We can add here, for example, a number of designs, but we have to configure also the remote source manager. For doing that, we can also add a Python script for updating individual parts of our model. And we can also retain the data for later use, means that of the individual designs, we keep the main important results in an individual design folder. So we can just update that. I've prepared the results because this is running about 3 hours, this 100 designs. And if we go to the post-processing now, which will then appear after the DOE has been finished, we get the following view. We will get a 3D view of the response surface of the Metamodel, which has to be found to be an optimal for a specific response. So we see here now, this is the mass, which is an almost linear function with respect to the geometry parameters. We see that mainly the upper plate thickness, the upper beam thickness, and the lower beam thickness contribute to the mass. We get an overview on the right upper side of the individual sensitivities. You see we have 4 responses, mass and the 3 displacements. We see that we have an influence of the upper plate thickness to the mass, which is absolutely dominating. But we see that this upper plate thickness does not really contribute to the deformations. On the other hand, the lower beam thickness contributes mainly to the deformations, and it also contributes to the mass. And the lower beam height mainly contributes to the deformations, but not very significantly to the mass. So we see here the percentage how the variation of an input parameter contributes to the variation of the response value. This depends, of course, on the range we have specified at the beginning. So we see that we have a final column which is indicated by total. This gives us an information how good was the approximation. So how good was the prognosis quality, the coefficient of prognosis for the individual approximation model. So we have about 99% for the mass, which is almost linear in that case. We have 95% for the maximum displacement at 0 degrees, 93% at 90 degrees, and 88% at 180 degrees. So if you are not satisfied with that, I mean, you would expect that there is a 100% approximation quality, but this is not possible in all cases if we have numerical simulations due to numerical distortions, may be the case, especially in CFD analysis. On the other hand, we may have some parameter combinations which disturb the Metamodel somehow. We can check that in the so-called residual plot up here, so the mass was already perfect. Let's check the displacement at 180 degrees. We see this is the residual plot, and we have indicated already some designs which have here red color. We see that they do not agree as good as most of the black points with the theoretical values. So we see on the x-axis the original simulation data values. On the y-axis we see the predicted values coming out of the Metamodel. We see there are some points who might be an outlier. Let's check these points further. One possibility you should definitely use if you apply sensitivity analysis or optimization with optiSLang is that you may consider graphical outputs of the solver. Means that we used in these blocks an LPDL script just to plot the deformations, to plot the mesh to the design folder. And now, in the post-processing, we can consider that, and we can check if for the specific design deformation is somehow plausible. Yeah, so we can add these images. There is a possibility to enter external files. Here we entered a single pixel graphic. You can also use 3D outputs from ANSYS Viewer, from VColab, and so on. And then let's check these files in here. And if we go now through the designs, if you just click on a single design, we see the corresponding graphic from the design folder. We see, okay, here, black dots. There is some more, some less deformation, behave quite well. And we have individual designs which look a bit strange. So the main part of the structure is almost undeformed, and we have some kind of a local part which is highly deformed. In that case, this is a minor model error, so the model was not able to capture the full parameter space consistently. There were some combinations of parameters which behaved a bit strange, so we did not consider these designs in the sensitivity analysis. So they estimated rather huge deformations. So we just collect all of that designs. Maybe we are not satisfied, and then we can simply deactivate them. Here we have some further outliers. Maybe we may deactivate them. This you should do with your knowledge about the physical phenomena and so on. Be careful not activating real dependencies. So here we had some designs where the model behaved a bit implausible. We deactivate them, these designs. We see them now in gray. And then we can update the Metamodel of optimal prognosis up here in the using the MOP button. And then we get a new Metamodel without these critical design points. Let us check the values. Now we have about 90% for displacements in 180 degrees and 97% for 0 degrees. So it means that we have some increase in the approximation quality of about 2%. Yeah, so this is one typical workflow that you go through the designs and may deactivate them if they are physically not plausible. So with help of this Metamodel, now we can go a step further. We may analyze the individual objective functions we have discussed at the beginning. So with help of the sensitivity analysis, we can select or detect possible regions where our model behaves or simulation model may behave not very plausible. We may detect the most important parameters, so we can reduce the parameter space or the parameter number, which makes then later on the optimization much more efficient. And if we have mainly a high explainability, which is about more than 80% or something, then we can be sure that the model behaves quite well, so that the optimizer has a good chance to find a suitable design. So let us come to the next point, an optimization. So we had several objective functions. This is so-called multi-objective optimization. I just want to give a short overview on the optimization algorithms available in optiSLang. What is the overall procedure we recommend? Use the sensitivity analysis because this effort is not lost, because we can then get some information on how are the relations, does the model behave well, and so on. Then we can use the Metamodel in the next step also for a pre-optimization search optimization. Using the MOP, we may get a good first guess. If it's acceptable, then we keep that as a best design maybe. If not, then this may be the case if the approximation model is not accurate enough. Then we may follow with a direct optimization using one of the available optimization algorithms. So what type of algorithms are available? We have gradient-based methods that just go downhill based on the gradients, which have to be calculated or estimated. We have adaptive response surfaces, which is approximating a certain range in the design space and then going down where some improvement is found. And we have so-called nature-inspired optimization, evolutionary algorithms, swarm algorithms, which try to imitate the behavior in nature. What are the applications of these algorithms? Gradient-based methods, the classical mathematical approaches, they can be applied if the objective function and the constraints as well are smooth functions. This is often not the case for numerical analysis, especially if you think about coarse remeshing, if you think about CFD analysis, and so on. Then it might be quite difficult to estimate the gradients consistently, and then the optimizer may fail. But they can be applied quite well for an optimization on a metamodel, because a metamodel is a smooth mathematical function. They could be applied there. The adaptive response surface method does something similar. It will approximate a certain region, it will shrink, and it's a very good balance between robustness and efficiency, and it's applicable for up to 20 dimensions. And in cases where you have quite high number of discrete parameters, binary parameters, and you want to enable a global search, we can apply nature-inspired optimization. On the other hand, we may have special optimization tasks, like in our case, we have a multi-objective optimization task. We have two optimization goals, which may be in conflict to each other, but we don't know in advance that. We have to analyze. So we may formulate several objective functions, and then we want to analyze how is a possible compromise. What do I invest in F1 if I want to improve F2? Like here on this black line, you see if I increase or decrease F1, that's an improvement. I have a decrease, which is a worsening of this F1 function. And we should find a compromise. The white dots are not interesting because we find always solutions which are better in all of the objectives then. So we are interested in the black dots spanning the so-called Pareto frontier. This Pareto frontier can be analyzed just by nature-inspired optimization efficiently. In order to support the user, we have developed a so-called decision tree in the wizard, which helps the user to decide which optimization algorithm is the best one for my specific situation. It considers the number of and the type of the input parameters. This is done automatically. Number of constraints, objectives, also automatically. This just comes from your formulation. And it considers three user settings. The analysis status, if it's a pre-optimized design or if you should search globally. Amount of failed designs, if you assume that there are some failed designs maybe during the solver evaluation. So this can be simply just unavailable license. So we don't want that the algorithm will stop there. And of course, the solver may have some distortion in the numerical analysis. So we may have some solver noise. And then using or based on a traffic light, optiSLang will recommend you a suitable algorithm with respect to your setup and the settings or the information we got from the problem itself. So now let us come back to our example. Let us perform a multi-objective optimization on the metamodel first, because this is quite efficient. If you have already a metamodel, then this is more or less for free. You don't need to run any solver call with a real model. We want to minimize the mass and we want to maximize the displacements. So let us switch back to the workbench. We want to use the optimization module here. We do not link it directly to the parameter set now. We link it to the MOP itself. Means that we now consider the metamodel as solver. We keep the parameter properties from the MOP, and now we have to define the objective functions. In multi-objective optimization, we consider the mass as one, and the second objective we want to consider the deformations. Not just a single deformation, we want to consider the maximum of these three deformations. Let's take the maximum function in here between displacement and position 0, and the maximum between position 90 and position 180, and then we need to close the bracket in here, and then we get a value. In multi-objective optimization, we are interested in some diversity of the Pareto frontier. That's why it makes sense that we scale the two objective functions to be in the same range. So we have 200 for the mass and 0.1 for the deformations. So let's just subdivide the mass by factor 1000, and we get almost the same range. And then the multi-objective optimization approaches work much better. This does not change the optimization task itself, because minimizing the mass is the same like minimizing the mass divided by 1000, or just taking a different unit. Yeah, but this is internally easier than to understand or to be efficient for the algorithm. And then we go to the next step. We see that the gradient-based direct search algorithms are disabled because they are not available for multi-objective search, and the evolutionary algorithm is recommended. Let's finish the wizard. We see now the new container is linked to the MOP. Now we can update that container, and now optiSLang will execute the individual designs, not with the simulation model itself, but using the Metamodel instead. What is the outcome of this analysis? We will get this post-processing. We get an overview of the individual designs that have been calculated. This is a plot of the two objective functions, so-called Pareto plot. We see the objective function, the mass, and we see the maximum displacement. And now we see all the points. They form some kind of a data cloud, and we are interested in a minimum mass and a minimum displacement. That's why we are interested only in the points being on this so-called Pareto frontier. We can select best designs, and we get all of these Pareto optimal designs, which are all of them are best designs, not just a single design, because all of them are possible compromises. Now let us invert the selection and deselect all non-best designs. We deactivate them, and then we keep just all best designs left. So we get this Pareto plot on here. We have these two objective functions, and now we see what is the possible compromise between the mass and the displacements. We see that for a quite small mass of about 140 kilograms, we get a large deformation, and vice versa. And what could be now a possible compromise? This is a decision which should be done by the engineer or designer. Here we decided together with the customer that a maximum displacement of 0.1 could be acceptable compromise. So we decided to do this limitation, so we can click on a design which may fulfill these requirements. We have to say this is a design which is valid only on the Metamodel, which is not validated with the solver run so far. We need to validate that. But we can also study what happens if we go along this Pareto frontier. What happens? At the beginning, we have almost all design variables being close to the minimum. So we have a minimum mass but high deformations. Then we go through the Pareto frontier. We see that first the lower beam cross-section measures increase, and then the other beams come into the game slightly, middle beams, and so on. Yeah, and we can now select a certain design and recalculate that, or we may go a step further that we analyze a single objective optimization task by minimizing the mass and limiting the deformations to 0.1 millimeters. Yeah, so this was the outcome of this analysis. This was a decision made with the customer, so it depends on the individual optimization task. Now we go for single objective optimization. First, we use the Metamodel of the optimal prognosis for a first shot, which is then quite fast in the analysis. So let us link an optimization again to the MOP. We keep the parameters from the sensitivity analysis in here, but now we minimize the mass, but we limit the deformations as constraints. So we obtain then a single objective optimization task. We limit all three displacements to 0.1 millimeters in that case. So we have now a single objective optimization task, one objective function, three constraints. Let's go a step further. Then we see now the decision tree recommends us a gradient-based optimizer. This is the case because we are using the Metamodel and we have a single objective function. So it's assumed that we don't have failed designs. It's assumed that we don't have solver noise. That's why we get now a recommendation for the gradient-based optimizer. We finish the wizard and check the settings in the workbench. We see that here a specific setting is now valid, which is validate best design after calculation. This means the optimizer is running on the Metamodel, and then the best design on the approximation is recalculated with a real simulation model. This is strongly recommended because the approximation may be very good or maybe not so good locally. That's why we strongly recommend the validation of the best design. You can also do that for the multi-objective optimization, but in that case, we have to validate all designs of the Pareto frontier, which may be more time-consuming. So in this case, the simulation or the optimization on the MOP is quite fast, and then we just need to run a single simulation model. So let us come or switch to the prepared results. We see that we get here fast convergence. But we get some deviations in the validation. So we get here the comparison. So the mass was calculated on the approximation with 181 kilograms, and it was validated between 185, so a bit higher than approximated. But what is more interesting, these are the constraints. So we have the three constraints that the deformation should be smaller than 0.1. We have 90 degrees, this is fulfilled. Also then in the recalculated design, we have 180 degrees, this is fulfilled. And we have 0 degrees, where it's fulfilled on the approximation model, but the validation slightly violates the constraint. So what could be a possible solution for that? We could redo a single objective optimization on the MOP by changing the constraint a bit, reducing the possible deformations. Or we can, if we are not satisfied with that, now do an optimization with a direct solver call. We may do the same, but not on the MOP. We do the same, just connecting the optimization to the parameter set. We import the parameters maybe from the sensitivity analysis. We may import the criteria from the second optimization, single objective. Then, in that case, the adaptive response surface method is recommended, since we now assume that there could be some solver noise. And then we start here direct optimization. We may consider the start designs if you like. So we may choose start designs from the sensitivity analysis and so on, if you like. and then we can start um, the optimization. In that case, I did not run the sensitivity analysis, so I don't have the designs available in here. In the prepared project, I had that designs available. So what is the outcome then? With a direct optimizer, we get some convergence there, starting with some initial design, maybe a good start design or not. And after 140 designs, we get that result that we could get a mass of 188 kilograms and a deformation which is smaller than 0.1 millimeters with a direct optimizer. So this was the overall procedure. So we get on the Metamodel, we get an approximation. We have to validate, but still we had some violation of the constraints. We had a reduction of the mass by 11% and by the deformation of 12% using the direct optimization, which was then time consuming again because we had to evaluate here at least 140 designs. We get a reduction of the mass by 9% and a reduction of the deformations by 17%. Now we get a design fulfilling the constraints. And if you go back to that plot, we see for the best design, for the best final design, we get a maximum lower beam height, some middle value for the thickness, a lower value for the width, and we get for almost all remaining parameters, we get the minimum values. Yeah, also for the upper plate thickness, and we get a middle beam width, which is about 1/3 of the parameter range. So hopefully you could see by means of that example that we could quite efficiently use sensitivity analysis in order to investigate the influence between the input parameters and the responses. We could reuse the results of that, the Metamodel of optimal prognosis, for multi-objective optimization in order to understand what is our possible compromises between the two objective functions, and then we could efficiently perform a single objective optimization. If you need more information, I would ask you to send an email to support@dynaro.com. There you can also get a trial license. And we are offering trainings, also e-learnings for worldwide users. So please visit our homepage, www.dynaro.de, where we have also a so-called RDO journal available online, which is a publication appearing twice a year with user case studies. Might be quite interesting. We have also a user conference here in Germany. All of these presentations are also available on our website, where you can study different types of applications and quite interesting presentations. So if you have questions with respect to optiSLang now, also to the examples, so please use the chat window, use the question and answer window, and we have some time for a discussion. So please ask your questions, or later on a possibility may be that you just write the support. We will provide you the slides and the example. The slides will be provided on the web page, and the example itself will be provided in our customer portal, and you will get an email with an access and so on.